Kepler has quite a few laws that relate to the motion of satellites, and we're going to be deriving one of his laws. I think it's really useful deriving equations in some instances because it shows where it's come from, and also it's a helpful mathematical exercise for practice. So let's start with two equations that both yield the force due to gravity, and we used this in a previous example. For something travelling in a circle, we know that the net force has got to equal mv squared on r. That's something that we've previously talked about. And for an object where that force that it's experiencing is the force due to gravity, that's equal to gmm on r squared. So we've previously talked about this. We eventually found if we divided both sides by little m and we multiplied both sides by r, we found that v squared was equal to gm on r. Now, we also previously found, and I'm just going to put this on the side here, that for something travelling in a circle, the magnitude of the velocity was given by 2 pi r over t. So let's replace the v squared in what we've previously done with 2 pi r over t. Let's continue over here. So we're going to have 2 pi r over t all squared. We've replaced that for the velocity, equals gm on r. Again, this is the velocity here. Okay, so squaring this, we're going to get 4 pi squared r squared on t squared is going to be gm on r. Now, let's get all of the constants on the right-hand side of this equation. And when I say constant, let's say we're looking at a particular planet and we're looking at moons or satellites orbiting this planet. So we're going to say big M is a constant. Capital G is the gravitational constant, that's not changing, and I notice we've got a 4 and a pi squared are also constants. So what I basically want to do is I want to get the 4 pi squared over the other side of the equation, but my r and my t values are going to change, so this r needs to go over the other side of the equation. So that means our final step is going to be, we're going to have r cubed on t squared equals gm on 4 pi squared. Now, this is an equation that we have used previously, but now you might have a better idea of where it comes from. So Kepler's third law, I think it's the third law, regardless, Kepler's law, the one we're focusing on in the VCE Physics study design, r cubed on t squared is equal to gm on 4 pi squared. Now that, whether you realise it or not, is a pretty neat thing. Let's just note, if you need to, I'm not going to note it down now, but r is the distance between objects, t, capital T is the period, capital G is the gravitational constant, capital M is an object being orbited, and I hope you know what 4 and pi squared are. Now, things of note. All objects orbiting a central body will have a same value for this ratio. We said if we're talking about a particular value of m, this is the object being orbited, this means that every single object, whether it's, if we're looking at the Earth, whether it's the moon or satellites going around the Earth, it's going to be the same value. And that value, this here, this is constant. So it doesn't matter whether we calculate r cubed divided by t squared for the moon or a GPS satellite or the International Space Station, so long as it's orbiting Earth, we will get the same number. If we find the radius and we find how long it takes to go around us and we do r cubed over t squared, it's always going to be equal to a constant, and the value of that constant is gm over 4 pi squared. The same's true for objects in the solar system, more specifically planets or anything else that's orbiting the sun, and we'll talk about that soon. So as I said, the second note here, this ratio depends on the mass of the central object and it is independent of the mass of the satellite. So it doesn't matter whether it's a teeny tiny piece of space junk going around the Earth or whether it's the moon in all its colossal glory, it's going to have the same value because it doesn't matter about the mass of those individual small objects. Another one of Kepler's laws that I just wanted to mention, it's not formally on the course, but it is nice. We've been focusing so much on satellites that we're assuming going in circular orbit. It's nice to kind of look at an elliptical orbit because this is more realistic and yeah, more realistic. That's all I'm going to say. Basically, something when it orbits very elliptically, it sweeps out particular areas, and it turns out this area here is the same as this area here. And these areas are a nice way of visualizing why, when an object's in a highly elliptical orbit, it moves much more quickly when it's at a closer distance to something, and much more slowly when it's a further distance from something. You can see in either of these scenarios here, this is 1 month's worth of motion for this random object here, some planet, maybe it's Pluto, I'm not sure. Actually, I think Pluto takes years to go around the sun, so maybe not 1 month, but some object here. If you're interested in this, definitely research Kepler's other laws. So again, a little taste of elliptical orbits and some of the physics behind that, but we mainly focus on circular orbits. So let's go back to that law we spoke about before. We specifically said r cubed on t squared has got to equal gm on 4 pi squared. It's an interesting formula. It's not often you see pi squared in things. It's quite nice. So here we've got some useful data about objects in the solar system. We've got a whole bunch of bodies, their masses, their radii, and the mean radius of their orbit, and the period of their revolution. So radius of body, we're not going to be using this value here because here this r cubed means the radius of orbit. I don't regret that table value, that column value is in here because it's nice comparing the radius of each of these objects. For example, one might look at these numbers, the Earth and the Sun, and say, oh, their radius is pretty different. But if you look at these powers, the order of magnitude is 2 times bigger. Sorry, not 2 times bigger. Well, the order of magnitude is 2. But numerically, the radius of the Sun is 10 times, not even 10 times, sorry, 100 times the radius of Earth. You think the Earth is big? The Sun, much, much bigger. So, still nice to have that data in there. But what we're going to be focusing on is this radius, the radius of orbit. This is little r that we referred to in this equation that we looked at before. And this is t, the radius of the orbit. We've got meters and seconds here, so good. They're the values that we want. Now, it turns out, I've given you a whole bunch of things here. We've got the Sun. This is the central object that's going to be orbited. So this is going to be big M in the equation here. And what things orbit the Sun? We've got the Earth, now not the Moon, that orbits the Earth, so that's different. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune. Pluto's not technically a planet, but it does orbit the Sun. So we can do these calculations. What I'd like you to do is I'd like you to select 3 planets. It can't be the Sun and it can't be the Moon. You can choose Pluto if you're happy to do a dwarf planet. I'm not going to discriminate there. I want you to confirm Kepler's third law here. So I want you to select one of these objects, perhaps Neptune, and I want you to do r cubed on t squared. And I want you to find out what that value is going to be here. Remember, this column was r and this column was t. And then I want you, to choose another planet, perhaps Jupiter. Maybe you'll do Venus. And I want you to again do r cubed for each of these. So this value, you're going to cube it. R cubed on t squared, so this value square it. And I want you to see what value you get. And you'll see whatever you do, whichever planet orbiting that central body, the Sun, it's always going to equal gm on 4 pi squared. Remembering, m is going to be the Sun. Any slight variation in your answer will merely be because we've only got things to 3 significant figures. But if you round it, it should be pretty much or exactly the same. So I want you to do that now. Select a couple of planets, in fact 3 of them, not the Moon because that is orbiting a different body, that's orbiting the Earth. And I want you to convince yourself of this. Now after that, I want you to find out the value of r cubed of t squared of the Moon. And I want you to think about what I said previously, rewind if you had to. What can be said about any other artificial satellites orbiting Earth? So I want you to pause and have a go at that. And I'm going to put a point here to help you with this if you're not sure, which you can listen to after you've paused. Okay, I hope you've paused. So any other satellite that could be natural or otherwise, we'll have, so I should be more specific, any other satellite orbiting Earth. Just going to fit that in here. We'll have the same value of r cubed over t squared. So that's really handy. We can use this value of r cubed over t squared to figure out the average speed of the Earth around the Sun. Actually, do we need that? If we have v equals 2 pi r on t, sorry, we don't need that. We're going to just use this. We're going to figure out the average speed of the Earth around the Sun. We're saying average speed because the radius of Earth does vary. It's an elliptical orbit, but we're going to do an average, assuming that it's a circular orbit here. So this velocity is equal to 2 pi r over t squared. So let's look up what those values were from the table. So the table tells us that our radius of orbit is 1.5 by 10 to the 11 meters, and our period is 3.16 by 10 to the 7. Now, if you're not sure about that, that is 60 minutes times 60 seconds times 24 times. For the purposes of the exam, you need to use that a year is 365 days. I've done 365.25, including a few more sig figs here just to double check, and that checks out. But remember, if you have to talk about a year in the exam, it's 365 days, 3 sig figs there. So let's actually calculate what that is. Alrighty, popping that into our calc, double checking what we've got. I get, if I do this to 2 sig figs, oh my gosh, that is crazy. It's going to be 3.0 times 10 to the 4 meters per second. Now, out of interest, I could have written that as 30 by 10 to the 3. And the reason I mention that, 30 by 10 to the 3 meters per second, that's a 3. I could write that as 30, and 10 to the 3 is kilometers, or well, 10 to the 3 is kilo. So that means 30 kilometers a second. Hold on tight, everyone. We are traveling at a very fast speed around the Sun. We don't feel that for a few reasons we're going to talk about within a future area of study. Luckily that we don't, because that would be very uncomfortable, I think. But yeah, we're going pretty fast. Okay, a critical question that you need to be able to do here, and we've spoken about this quite a lot. This is one of those graphing questions, and you need to be extraordinarily careful. A lot of things you need to do correctly to get the marks here. So some students have collected some data on the orbital period t and the orbital radius. They're using capital R here, that's fine. Are of 5 of Saturn's moons. The results are shown in the table below. Assume that the moons are in circular orbits. Very good. So, bunch of moons. I'm not going to attempt to say their names. We've got the orbital period in seconds. So this is t. And the orbital radius they said is r. Now they very generously have given you the values of t squared and r cubed here. They could have asked you to do that. Okay. So we have been provided with a set of axes here. And we need to plot a graph of the observational data t squared versus r cubed. So very kindly, they've told us that this axis needs to be t squared and this axis needs to be r cubed. We're not going to reverse those. Or at least try not to, please. We need to include a scale on each axis and we need to draw a line of best fit. So we definitely need our pencils out ready to go, and we'll need our rulers in a moment too. Looking at the values that we've got here, I notice just like when we look at graphs and we have to look at the axes to see if there's some weird units, I notice the units here. This t squared, it's this value here doesn't just mean 0.66, it means 0.66 times 10 to the 10 seconds. So that's what this gap here is trying to tell us. It's saying please fill this in. You'd be surprised how many students don't fill this in. So when there's a big gap, try and assume it's telling you something. So we'll put 10 to the 10 here. That seems reasonable. If we're looking at the r cubed values, I notice it's 10 to the 24. Gosh, that's really big. So we'll put 10 to the 24. Now we need to look at the kinds of values that we need to graph. We need to go from 0.66 all the way to 15 on t squared. Let's look at what we've got here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I can reckon we can go up by ones on this axis here. If you wanted to be lazy, you could do a bit of 2, 4, 6, 8 action. I should have used my pencil there. I'm going to stick with it because I can erase this, but please use a pencil. Especially for doing a scale. The number of times students start counting and then they realise, oh, I didn't actually have enough room for this. So the rule for the last time I marked these is you had to use at least 50% of this scale. My recommendation would be use as much of it as you possibly can. Use the space here. It's going to be easier for you to graph if you're not trying to cramp it all up. Seriously. Okay, that was relatively painless. Again, use pencil. Let's now look at the values that we need to plot for r cubed. This one is a little more intense. I noticed that we've got 6.40 as our smallest one and 146 is our biggest. Ugh, that's a bit yucky. Okay, I've counted the number of divisions that I've got here. I forgot how many it was though. 2, 4, 6, 8, 10, 12, 14, 16, 17. Given we need to go to a maximum value of, what was it, 150-ish, I reckon going up by 10 for each one, I'm just going to label the 20s here. 20, 40, 60. So that's quite nice. Again, we've used as much of that scale as we possibly can. And I literally look at my maximum and minimum values. Technically, we should always be starting with 0, so I don't know why I thought about my minimum value in retrospect. We need to think about our maximum, and we need to have room on the scale. You do not want to be trying to like draw this longer and have divisions here. Trust me, don't do that. So think of the maximum value, look at how many spaces that you've got here, and use that to make an appropriate scale. This would get full marks. Not to toot my own horn. So we now need to go ahead and plot these values. This you need to do really, really carefully. Now, the trick is, we know the physics about this. We know, we're using a capital R here, but r cubed on t squared, we know it's equal to a constant. And that constant, just out of curiosity, I'm not sure that's the right word, that constant is gm, and that would be mass of Saturn. They've not told us it, but we could technically discover that. I'll talk about how, if the question demands it. But that's a constant. So that means if we do r cubed divided by t squared, and it always equals the same thing, we're going to have a straight line. So we can sort of be a little sneaky in how we do this. We're anticipating a relatively straight line. It may not be perfectly straight. There might be slight variability in the data, so they sometimes do that. Let's plot it and see how we go. But it's going to be a straight line. I'm going to do it not on camera because I'm going to be scrolling up and down a lot, which will drive me slightly insane and maybe you as well. But plot carefully in pencil. Alrighty. So using a ruler and a pencil, here's what I've come up with. It's pretty close to being a full straight line. That's pretty good. I've included an arrow on the end because that could technically continue off. I can't have it going past 0 though, because that doesn't actually make any sense. So we'll just erase part of that there. That's better. Now, pro tip. If one of your points was severely off, but you knew you were expecting a straight line, perhaps you could put a note on your data sheet that if you plot r cubed on the horizontal axis and t squared on the vertical axis, for objects orbiting the same body, you will get a straight line. And it should technically go through 0, technically. If there's some sort of systematic error that we'll talk about, perhaps it wouldn't, but that, I'm getting off on a tangent. Anyway, if you're expecting a straight line and you'd been plotting along and you saw you had one point down here, that would maybe be an opportunity to re-examine that point. You might have made a plotting error. So having that in mind can actually mean that you can sort of self-check something as you go along. And indeed, when I was drawing this line, it made me double check that all of my points were pretty good, and this would get full marks. Was there anything else I wanted to mention on this? You don't need a title up here or anything. Whoop, not drawing. There we go. You would if this was technically a lab report. Actually, no, let's just do it. I think it's good practice too. So let's put r cubed versus t squared. It is good practice. I take back what I said. Include a title on top there. So the points for this, it would have been making sure we plotted things on the correct axis. Some people still confuse the t squared and the r cubed on this particular year, even though it was labelled for us. So you need to be really careful with that. Including an appropriate scale, plotting the points correctly, and including a correct line of best fit. Pretty good question. Okay, this next part is a pretty common style of question here. We need to calculate the gradient of this line of best fit. Now, to do this, there's a couple of ways you can do this. My preference is make sure that you choose 2 points that are already present on your line, and choose those 2 points that are as far apart as possible. So I notice that this point looks like it's exactly on the line, and this point is exactly on the line. So I can use our y2 minus y1 on x2 minus x1 formula here. So gradient m and let's look in the table at what those 2 points I circled corresponded to. It was the second point here, and it was the last point here. Now we need to be careful. T squared, that corresponded to our vertical axis. So these are like the y values in inverted commas. And r cubed was on our horizontal axis. So that is like our x value here. So we need to use these values in the table below. I'm going to snip it so I can refer to it and show you. Okay, so I've just popped that there just so I can refer to it because I can't flip pages like you can. So like we said, these are the y's and these were the x's. So my recommendation again is choose 2 points that the line of best fit already perfectly goes through. Make sure those 2 points are as far away as possible from one another, and then use this formula here. I'm going to go ahead and pop that in now. Oh, everyone, I just made a fatal error. And this is an error we talked about when we did transition. So, did you spot the error? These values here had multipliers. Oh, silly me. That's okay. We'll learn from this mistake. So, this wasn't 15.2 and 1.59. It was times 10 to the 10. And these values here weren't 13.5 and 146. Both of them were multiplied by 10 to the 24. So let's put that in here. I'm going to pause because I've forgotten which one's which. Alrighty, the top values, double check and make sure I've got this correct because I'm a little bit tired. But the top values were multiplied by 10 to the 10 and the bottom values were multiplied by 10 to the 24. That's a critical error I just made. So let's see if we can fix this calculation and get our proper value of the gradient. Well, this changes things significantly. That to 3 sig figs, we've still got that 104, but now it's 1.04 by 10 to the negative 15. I find it reassuring looking at the statistics on this sometimes. There was some variation for this answer. So we got 1.04. That's fine because it fits within the values that they've given here, in between 9.9 by 10 to the negative 16 and 1.1 by 10 to the negative 15. And I did exactly what the last line says. It says, while most students realised that a gradient calculation was required, a significant number left out the exponents. So I nearly lost that mark. I would have been one of the 41% of people that maybe got 1 mark. That's a bit funny. Now this question is a little more difficult. It's relying on your answer from part B. So even if you weren't certain of your answer from part B, you need to get a number, pop it in there so you can use it in part C. This bit is a little more challenging. But basically, because we've got a straight line graph, we're going to manipulate our equation. Now, the variables that we used were r cubed and t squared. And we previously learned during our discussion of Kepler's laws earlier on in this video, r cubed over t squared was equal to gm on 4 pi squared. Now, we noticed when we did our graph, what were we actually graphing? Let's look back. We had t squared on the vertical axis and r cubed on the horizontal axis. And we said that t squared was a bit like our y value and r cubed was a bit like our x value. And when we graphed these things, we got a straight line. So that means something important. It means that this is a linear relationship. I want to be able to manipulate this equation in a particular way. Now, what I'm going to do, rather than explain what I'm trying to achieve, I'm going to do it and then explain why I did it retroactively. So for reasons that hopefully become clear later, I want to take the reciprocal of both of these sides. T squared on r cubed. I've just flipped that first one, and let's flip the other side. Okay, so you may not be sure why I did that, but I need you to convince yourself that mathematically that means the same thing. Okay, so now what I'm going to do, I want to multiply both sides by r cubed. So t squared is going to equal, I'm going to put a big old bracket around this. We don't mathematically need it, but it's going to help in our discussion later. 4 pi squared on gm times r cubed. Now, why did we bother to do this? Why did we bother to rearrange this like this? Well, we said that t squared was like our y value. And we said that r cubed was like our x value. And you might recall that the equation for a line is y equals mx plus c. When you first learnt this, perhaps in year 8, you learnt that the number multiplied in front of the x is m. So that means this value here is m. The gradient of our graph is equal to this constant, 4 pi squared divided by g times the mass of Saturn. That is really helpful. This is something called graph linearisation. We manipulated our variables t and r so that we could end up with a straight line graph. This is the gold standard in physics, and if you're able to achieve something like this in your extended practical investigation, brilliant. So much awesomeness to be had there. So we said t squared was like our y value, and r cubed, I should have technically put a capital R here. Let's retroactively put a capital R. So t squared against r cubed produced a straight line. So we rearranged this equation to get t squared, which we said was like our y value, as the subject. That means by itself on the left. And we wanted everything else on the left. And we ended up with something times r cubed. Now we said r cubed was like our x value, so that means that something must be the gradient. Now if you're looking at here and saying, oh, if y equals mx plus c, what is c? Well, we don't have anything added or subtracted on the end, so that means our intercept should indeed be 0, as we noticed in our careful graphing before. So this all means that if we use the gradient here, that has to be equal to 4 pi squared over gm. So this means that 4 pi squared over gm equals, I'm going to write the gradient here rather than m, because you might accidentally think it's a mass of something here. So this means if we wanted to find out what m was, algebraically rearranging this, m is going to equal, I'm basically swapping m and the gradient. It's going to be 4 pi squared over g times the gradient. Now I've run out of a bit of room here because I was way too big on my calculations before. So that means 4 pi squared divided by 6.67 times 10 to the negative 11 times that gradient, 1.0, I'm going to use 1.04. Do I have any more decimals? I'm going to use 22, just a couple of extra ones. Whoop, times 10 to the negative 15. So that's the benefit of keeping a value in your calculator. You can grab those extra sig figs. Let's now calculate what it is. In fact, I think I'm going to use that value I previously had in my calculator. Alrighty. So there you go, here's the examiner's report for this one. And this has a really valuable point that I want to talk about a little bit more. I know this is a long video, so I'll finish it after this. But it talks about the fact, sorry, I don't have that quite in frame, that many students did a calculation here where they got the correct answer, but they didn't get full marks. The chief examiner has a pretty strong opinion on this. Just because you put the correct number in the box doesn't mean that you have gotten the correct answer. If you use an incorrect approach physics-wise or mathematically, you don't get the marks. So just because it's the correct number doesn't mean that you've gotten the correct answer and doesn't mean you get the answer mark here. So they've used the approach that we've used here. They rearranged the equation. Same values that we did basically. Please note that just because you have the right number in the box, it doesn't mean you have the answer correct. Chief examiner is very fussy on this.